So this is a continuation. This is part 2, the second half of the power analysis overview. And I just wanted to clarify one small change, and that is when I was talking about the critical value for the bottom pair of graphs. I misread it because the number was small on the copy I had printed out, but the critical value is 2.878 with the interpretation of whenever you would get a t value that was greater than 2.878, you would conclude that the two means were significantly different from each other. I had said 2.4 or something like that, but I just wanted to clarify so you weren't confused about what I was looking at. So in going to the next page of this power analysis handout, you're going to see some graphs that look really similar. In fact, the top two are exactly the same. We already talked about if you have an alpha level of 0.05, there would be 55% power to be able to show a significant difference if the diuretic has a 200 ml per day increase in urine output. And this is what we talk about when we refer to different effect sizes. The other two graphs at the bottom of this page, the original comparison is a 200 ml increase of the active drug. But if the drug was less effective and the increase was actually more on the order of 100 mils per day, you can see that's graph number C. You can see that the critical value still is at 2.101, but the percentage of T values that are to the right of that critical value is much smaller because the mean of 100 mil increase is more similar to a mean of 0 mil increase, which is what would happen under the null hypothesis if there was no difference due to taking the active drug. So with that smaller difference or smaller effect size, you would get a power of 17% because only 17% of the time would you have values that were beyond the critical value of 2.101. And then at the opposite extreme, if the diuretic were super effective and increased urine production by 400 mils per day, then you would get a huge shift to the right of the distribution of the T values if the alternative hypothesis of this 400 mil per day increase were true, which would put actually 99% of the possible values to the right of that 2.101. So one of the things we talk about in the context of power analysis, besides changing the alpha level, is also changing the effect size or changing our assumptions about how much of a difference we think the intervention, in this case a diuretic, may have on the outcome. And then if you go to the next page, there's one more set of graphs and then we'll be done with this part of it. Move up a little bit. Okay. Again, the first two graphs are exactly the same as what we've had before in the previous figures. So 55% of the time, if the increase is 200 mils per day for the active drug, and what the extra bit of information that we're given in this top slide is that this is functioning under the assumption that the sample size for both the treatment and control group is 10 patients in each group. And then what happens is if you have a larger sample size, you have a better understanding of what the underlying population looks like. So not surprisingly, you have a greater level of power to be able to show group differences if they truly exist. So the top set of graphs are the situation with a sample size of 10 per group. The bottom set of two graphs is what happens if we increase the sample size to 20 per group. So doubling the sample size has the effect of decreasing the critical value of 2.02 down to 2.025 from 2.101, just because we have a better understanding of that underlying population, which has, again, we're still assuming the 200 mil per day increase due to the active drug. But given that smaller critical value, now we have 87% of the possible T values are to the right of that critical value, which indicates a power of 87% compared to 55% with a sample size of 10. So doubling the sample size for both groups had the effect of increasing the power from 55 to 87%. Then next we have, this is kind of a wordy summary, and really the reason that I have it in here is to give you an example of what a typical power analysis statement might look like. If you, not that you would go away from this class and write a power analysis statement on your own, or determine what the appropriate power analysis would be for your project, but this is to give you an idea of the pieces that need to be in a complete power analysis statement. So we already talked about it a little bit, but power depends on the magnitude of difference expected, which is the effect size. That is, in our example, the difference between 100 versus 200 versus a 400 mil increase in urine production. The variability of the measurements, which has to do with, how variable are each of the subjects that are included. How variable is their response to an intervention? So, for example, if we didn't talk about this specifically in one of the examples, but for example, if the diuretic has an average effect of a 200 mil increase, but for some people the increase is 0, and for other people it's 400. That's going to be more difficult to show a group difference compared to a placebo control condition than if the average of 200 really varies around, say, 180 to 220. Because there's just that increased variability means that we have a less of a good example of how a typical person might respond to that drug. And then the third thing that it depends on is the sample size. That's the example that we just looked at. In general, this is really similar to Part B, that the larger the sample size we have, the more we understand about the underlying population. So all other things being equal, the power is higher in that situation for higher sample size. So how can we maximize our power? If we assume that the magnitude of difference with the effect size is large, if we assume that the variability of measurements is relatively small, and if the sample size is as large as we can make it. Now, sometimes we don't have control over any of those things, but how those different quantities change will influence what the expected power is by the time you finish your estimate. And I should say that also is that power analysis, that strategy is really a planning strategy. We wouldn't look at a power analysis once we had already collected data and looked at differences between groups or that kind of thing. We would say, a student might say, a faculty member might say, I want to look at the difference between, an active drug and a control, between this intervention and the control. It's whatever the question may be. I have a research question that I want to answer that will be answered via hypothesis testing. And as I plan this study, how will I know how many subjects to have? And so we would talk about it in the planning stage, how to make educated guesses on the effect size, the variability, and the sample size that is achievable for the study that we have. So the rest of this page, I'm just going to skip over the words because there are a lot of little details here that maybe are beyond what you would find useful personally. But this example just shows how a power analysis statement would include all of those little pieces, what you're assuming when you make that statement about what the power is. So in the context of a two-sample t-test, if we call D the difference in means divided by some estimate of the standard deviation of the observations within those two groups, then we can use that D, our best guess of what D might be, to choose what is a reasonable level of power for the sample size that is feasible for our study. So in that context, a typical power analysis statement might say something like, with an alpha level of 0.05 and 64 subjects per group, the power of the two-sample t-test to detect a significant group difference will be approximately 80% if the ratio of the difference in means to the standard deviation is at least 0.5, and so on. Cohen is typically referenced in this context because he was the original person who developed a lot of the methodology behind power analysis estimation. But you notice the things that I mentioned there were the alpha level that I specified, what statistical test I'm using, the effect size that I'm assuming, the power that I estimate that I will get, and then citing Cohen would be a typical thing. Now, Cohen has a book that's kind of like the Bible of power analysis. And you'll be able to see this better if you print this out. It's not really clear on this video. But essentially, this book shows the estimated power for a variety of combinations of D. Remember, D is the difference between the two group means divided by the standard deviation. And then N, which is the sample size. N is the first column there. And that's the sample size per group. So the larger I make D, and then the body of the table has the actual power. So you can see if you look across the top that the larger D is, which is like an effect size here, the larger the effect size is, the power goes up as well. And the larger the N is, the power goes up as well. So if you go across the row or down the column, the power is increasing. I have one entry that's circled here, just as an example. So from this book, if I had an effect size of 0.5, which is what the top of this column is, with 72 subjects per group, I would get an estimated power of 85%. So with an effect size of 0.5 and 72 subjects per group, using a 2-sample t-test, I would get estimated power of 85%. Yeah. And why did I choose that 0.5? Cohen considers a 0.5 in this context, in the context of a 2-sample t-test, to be a medium effect size. And so typically if students come to me or if faculty come to me and they say, I want to do this project, I'm not quite sure how many subjects I can have, and I'm not quite sure about what type of effect size, then we usually aim for medium and then hope that works out okay in terms of the number of feasible subjects that can be included. And so that's why I chose that. But the last couple of pages I'm going to show you, this page here that says Enquiry Advisor, this is some software that I use. So I first showed you kind of the old school method of using the Cohen book. But when I do power analysis for students or student projects or whatever, I typically use the software that's called Enquiry Advisor. And with the software, I'm able to type in what I think the effect size is, the proposed sample size, all those details, the alpha level, of course, and then the estimated power comes out. So it's based on the same methodology as the Cohen book. It's just there I have more control over the combinations of effect size, sample size, and power than I would otherwise have. So, for example, I'm able to use this software to show how power changes as I change different attributes. For example, again, this is the 2-sample t-test, and with an alpha level of 0.05, and it's a 2-sided test, and the difference in means about, the effect size, basically, you can skip down to that. The effect size is 0.5. I would have 80% power with 64 subjects per group. If you look at the table here, it's a little bit hard to see, but right above the circled entry, if you go up 2 spaces, this is 80, which corresponds to 64 subjects per group, which is exactly what the software is indicating. So I can say, what if I leave everything else the same, but I change alpha to 0.01? We know from having talked about this before that should decrease the power because I'm making it more difficult to reject the null hypothesis, and in fact it does. So the power drops from 80% down to 58% with everything else being the same. So I can go back up to 0.05 for alpha level, change to a large effect size, again using Cohen's definition of a large effect size, and with the sample size of 64 per group, I would have 99% power. So virtually, I would be virtually assured to find a group difference if one existed. And then this last column is what happens if I change to a small effect size. And the power with that assumption would drop down to 20% power. So a small effect size would be something that would be more subtle to be able to detect than a medium or a large. Finally, the last little bit is just, this is a test of correlation that I can also get the estimate of using Enquiry Advisor. And you can see